Yes. Am I audible? Am I audible now? Can you hear me?
Yes, sir, you're audible right now.
Okay.
Yes, sir, you are asking about distance of closest approach, right?
Yes. What is distance of closest approach?
Yes, sir. So basically, distance of closest approach means when the two objects are like their distance between their centers are like tangent to each other.
So suppose helium nucleus is approaching, right?
Yes, sir.
Now this helium 2 plus, this is alpha particle, which is approaching this nucleus.
Yes, sir.
So this nucleus is also positively charged, right? Nucleus is also positively.
Positively charged.
Now, as the nucleus is positively charged, nucleus is positively charged. So, nu it will repel. It will get a repulsion when it will reach more closer. The more closer it will reach, it will get more repulsion because positive will be repelled by each other, and as per the Coulomb's law, you will get a Coulombic repulsion. So it will not able to touch what this alpha particle will do. It will go close. So after reaching a very close distance, it will stop. After reaching a very close distance, it will stop. Right? It will stop. It will not move further. So this distance between this nucleus and the alpha particle where it will stop, this is called distance of closest approach. This is called distance of this is called distance. Now we can find right. So this is the closest distance. Now, how will you find this closest distance? So we'll use the energy consideration. We'll use the energy consideration. What is energy consideration?
Sir,
What is
kinetic energy.
right? So when the helium was moving towards the nucleus, it is having kinetic energy, and that kinetic energy is half mv square, right? Now this
Yes, sir.
kinetic energy gradually is converting to potential energy because due to the repulsion, it is moving against the repulsion, so doing the work against the repulsion. So this energy is gradually stored as the potential energy. Like you can think of a compression of a spring. If spring is there, you will just if this ball is moving with a velocity v, its momentum is mv. Now it will strike the spring, so gradually it will compress. At a particular distance, it will stop. Again, spring is compressed now. So compressed spring will push it back again. So it will reflect back from there. It will get a backward push. So at the closest approach, at the closest distance, what will happen? The speed will become zero. It will stop. So where the energy is now this kinetic energy is converted to the potential energy. Kinetic energy converted to potential energy. Now, what is potential energy? Electrostatics potential energy formula. What is potential energy? You understood the concept?
So
Why?
that is mgh.
No, mgh will be when the object is at a certain height from the ground, and that is
Sure,
due
sure.
to gravitation.
Mhm.
Potential energy due to gravitation. Here, electrostatic potential energy that we have learned in chapter number 2.
Okay, sir.
So, if two charges are there, then what is the potential energy between them? Potential energy is basically bringing an object from infinity to that point, the work done. The concept of potential energy is. So here, if we shift from this
Yes, sir.
particle from here to here, so when it is at a distance r from another charge, so how much is the potential? Let's say two charges are separated by a distance r. What is the potential energy? Formula K Q1 Q2 by R.
q2 by r. Yes, sir.
This is potential energy.
Yes, sir. And the charges are if identical, then k q square upon r.
Yes. So here your Q1 is the charge of this helium and Q2 is the charge of the nucleus, right? Q1 is the charge of helium and Q2 is the charge
Sir,
of,
it would be kq upon r, right? Not why you are
that
considering
is
both the charges.
that is potential. There are two terms if you remember. One is potential energy and another is potential.
Oh, yes, sir. Yes, yes, sir. Yes.
Potential is charge per unit length. Means
Yes, sir.
per unit charge. Potential energy per unit charge is potential. So that will be only kq by r. This is your potential. This is
Yes, sir.
potential. But potential
Yeah.
energy is k q1 q2 by r.
Yes, sir.
So in this case, what is q1 and q2? Q1 is the charge due to the helium, Q2 is the charge in the nucleus, right? So that this energy, potential energy, that this will be equal to your kinetic energy of the helium, initial kinetic energy of the helium. So what we can
Yes, sir.
write? We can write the equation like this, that your kinetic energy is, or we can write like this, EI equal to EF. EI is the energy, initial energy, EF is the final energy, that is the potential energy. So what is EI?
That is half mp square.
Yes. So this is the kinetic energy. And what is potential energy? Potential energy, let us write the potential energy here. Potential energy is 2 ZE square, that is K into, what is the Q1? Helium, how many, what is the charge of helium? Helium charge is 2e, right? Means
Yes, sir.
plus 2 means is the same as 2e, plus 2e. Proton and electron charge is same basically, right? So Q1 is 2e, and what is Q2? What is the charge of the nucleus?
That is
The
zd.
nucleus is JD, right? Z is the proton number into E. Suppose sodium. What is the charge of the sodium nucleus? Sodium nucleus is having 11 protons, right? So what will be the charge? 11e. Proton charge is also equal to the charge of electron. Electron charge we just take negative, proton charge we just take positive, right?
Yes, sir.
So So here Z means atomic number. What is Z here? Z is the atomic number into electron charge of electron. So atomic number into charge of electron. So that is your final energy. So we can write that this final energy is by R. R is the distance, let's say D by D. So we can write K 2ZE square by D. This is your EF. This is your EF. Now this is equal to your half mv square. That is kinetic energy. So if we cross multiply and find the expression for D, so you will get D equal to this 2 here to multiply 4 and okay, not need to multiply because what is the closest distance closest approach to the nucleus of 7.7 MeV alpha particle. That means kinetic energy is given 7.7 MeV. So directly we'll put in place of this 7.7 MeV, right? So what we'll do, we can directly write K is 9 into 10 to the power 9. 2 Z is, what will be Z? It's a gold nuclei. So gold nuclei, because alpha particle experiment, the nucleus is what? Gold. The Z of gold is 79. E square is E. E is 1.6. Charge of electron is 10 to the power minus 19 coulomb square. Fine. And divided by distance. So distance though we have already taken, divided by the energy, kinetic energy. This one is all divided here. D is here. So kinetic energy is what? 7.7 MeV. If we'll convert to joule, because SI unit is joule, right? So kinetic energy given as 7.7 MeV. How will you convert to joule? How will you convert to joule? M means what? Mega electron volt. M means mega electron volt and mega means 10 to the power 6. Okay. And what is EV to joule? How will you convert EV to joule? How will you convert EV to joule?
Sir, we can use 1.602 into 10 to the power minus 13 joules.
Minus
13 joules, sir. 1 mega
13.
electron volt.
Okay. So you are directly multiplying. Okay. So mega
Yes.
electron volt, mega is 10 to the power 6 basically, and 1 electron volt is charge of electron. So 1.6 into 10 to the power minus 19 joule. So 19, if you multiply
Yes, sir.
10 to the power 6, it's 10 to the power minus 13. You are saying directly. Okay. So now 7.7,
Yes.
1.6, if you multiply, you will be getting basically, it will be coming up 1.2 into 10 to the power minus 12 joule. Right.
Yes, sir.
So just we'll put it in place of the kinetic energy, 1.2 into 10 to the power minus 12 joule. So we'll be getting the distance of closest approach. After multiplying, approx will be getting 3.84 into 10 to the power minus 16 into Z means 79. If you multiply whatever the 79 or 78 for any atomic number, you are getting a common expression for a D. 3.84. These things will be same, only Z value will be different, so you will be getting different closest approach distance. So the formula is half mv square K2ZE square by D. This is the formula for distance of closest approach if the kinetic energy is given. So you can directly divide it. If it is not given, mass and velocity terms given. So you can put the values of mass and velocity. Then you can divide them. Is it clear?
Yes, sir.
So this is called distance of closest approach, and we can calculate this using the concept of potential energy and kinetic energy, this distance of closest approach. Now we'll find out the electron orbit. So Rutherford told that electrons are revolving like planets revolve around the stars or sun, right? This is what Rutherford model was. But there was a serious difficulties in that model that will come into, we'll discuss that if it is revolving like planet, so what will happen? Electron, if it will accelerate because it's changing the direction, so it is accelerating. So accelerated electron loses the energy. There was some certain experiment that comes up with the theory that, or the result that, the suppose an electron is revolving around the nucleus like a planet revolves around the sun, so it is accelerating because it's continuously changing the direction. So it is accelerating. So accelerated electron, what will happen? It will radiate energy. So when the energy will be radiated, it will no longer be in the same orbit. So gradually it will come and fall on the nucleus. Right. So this theory, that's why means was that time not accepted properly, Rutherford model of the your atomic model. So people thought that electrons, if they will fall on the nucleus, so it will not stable, it will not be a stable atom, but it's not happening. Atoms are stable. So they thought that then what are the positions of the electrons? Does the electron revolve in around the nucleus in a fixed orbit or in a variable orbit? Right? So this question they kept on thinking. Now Bohr's come up with the idea with a fixed stationary orbits, that electrons revolve around the nucleus in a fixed stationary orbit, and we will come into the Bohr's model in detail in the next part. That also you might have read with all this in chemistry. So the Bohr's come up with the idea that the electrons revolve in a stationary orbits and also fixed distance, and the distance will be come and discover that this distance will be decided by the angular momentum of those orbits will be possible whose angular momentums are nh by 2 pi. This is the concept from the Bohr, that they are discrete energy levels or discrete orbits possible whose energy levels are nh by 2 pi. H is the Planck's constant, right? So those this thing will come up. Now, what are the electronic orbits possible? So let us find out the electronics, the orbits of the atom where the electrons are revolving or electron stays around the nucleus. So Rutherford nuclear model of atom, which involves classical concepts, pictures the atom as electronically neutral sphere consisting of very small, massive, and positively charged nucleus at the center of, surrounded by the revolving electrons in their respective dynamically stable orbits. The electrostatic force of attraction Fe between the revolving electron and the nucleus provides the requisite centripetal force Fc to keep them in their orbits. So then the Coulombic force comes into picture. People thought that which way we can give some description to the atomic model so that electrons is not falling but electrons in a stable, revolving in a stable orbit. So people come up with the theory that the electrostatic force of attraction between the nucleus, because nucleus is positive and electron is negative, right? So there will be attraction between the positive and negative part. So people thought that this electrostatic repulsion or electrostatic attraction, that is Coulombic attraction between the electron and the nuclei, will be equal to its centripetal force. Centripetal force means because the electrons revolve around the nucleus, so it will have centripetal force. Any object, if revolves in a circular path, it will have a centripetal force, right? So this centripetal force is provided by the Coulombic attraction. Coulombic attraction means the
Yes, sir.
attraction between this charge and the nucleus. Nucleus, protons are there, so positive charge, and this electron is a negative charge, right? So electron is a negative charge and nucleus is positive, so it has nucleus is positive, so it has like it has proton, so it is positive charge. So what is electrostatic force between the electron and the nucleus? We know Coulomb's force. So what is Coulomb force? That is your Fe we are writing. That is K Q1 Q2 by R square. That is the electrostatic force. Yes or no? This is the electrostatic force between the charge and the nucleus. So what we can write? What is our Q1? Now Q1 is the electron, and what is Q2? Q2 is the nucleus, right? So Q2 also we can write E, let's say charge of the, or JD we can write for hydrogen atom. For hydrogen atom, your Z value will be also 1. That number of proton is also 1 for hydrogen atom. If we take a simple case of hydrogen, so for hydrogen atom, your Z will be 1. That means Q2 also 1, because in the nucleus also 1 proton is there in hydrogen. Getting? How many protons are there in the nucleus? How many protons are there in the nucleus?
Sir, 2.
Hydrogen atom.
Oh, sir, 1.
1. 1. In hydrogen atom, only one proton is there, right? So one proton means what is the charge? Charge of electron, because proton and electron charge are same, opposite, just
Yes, sir.
same charge. So Q2 is also E. Q1 is the charge of electron that is in the surrounding of the nucleus. So K, Q, E, E, Q1, Q2, Q1 is E, Q2 is also E. So K, Q1, Q2 by R square. R is the distance, that is the radius of the orbit. So K, Q1, Q2, R square, that is your Fe. That is your Fe. Now we can write that this electrostatic force that is Fe equal to K E square by R. We can write that K E square by R equal to centripetal force. What is centripetal force? Any object, if it is revolving around the
MV square upon R, sir.
yes, any object, if it is revolving around the nucleus, it will have a centripetal force. It will have a centripetal force. So what is the value of that centripetal force? The centripetal force will be mv square by r. So K E square by, this is R square, right? K Q1 Q2 by R square equal to mv square by r. So r are cancelled out. So we can get from here, we can get the radius. So cross multiply. So radius of the electronic orbit, r equal to, it's K E square by mv square. This is the radius of the orbit. So electron orbit means in which orbit, or what is the distance from the center where the electron will revolve around the nucleus. Is it clear? So we got an expression for the radius. Similarly, from this expression, we can also get that in that orbit means this one is the orbit, this is the nucleus. So in that orbit where electron is there, what is the speed of electron? Also from this equation, we can get the speed of electron, like v we can get, v square we can get, and then we can get v also. Is it clear?
Yes, sir.
Okay. Now we'll write. So this is what radius we got. Now we'll write the kinetic energy and potential energy. We'll write kinetic energy and potential energy. So what is kinetic energy? Kinetic energy is half mv square. And what is v square we got from the last? This is the v square we got, right? K e square by r square is mv square by r. So k e square by r square equal to mv square by r. So what is your mv square value you are getting? Mv square is k e square by r. This is the mv square value you are getting. Clear? So mv square value you are getting, that is k e square by r. So you can write kinetic energy equal to half mv square. That mv square is k e square by r. K e square by r. Right? This is the kinetic energy. So this is the kinetic energy here. That e square by 8 pi epsilon naught. From where 8 pi epsilon naught is coming?
Yes, sir.
So from where this 8 pi epsilon naught is coming? We have written kinetic energy is half k e square by r. In the book it is written k means kinetic energy is e square by 8 pi epsilon naught r. So how they have written this?
Sir, they are multiplying 2 in the denominator.
Multiplied,
Multiplying 2 in the denominator.
and then the value of k they have replaced. What is the value of k?
So the value of k is 1 upon 4 pi epsilon naught.
Yes, the value of k is 1 by 4 pi epsilon naught. So we can write k equal to half 1 by 4 pi epsilon naught e
Yes, sir, I
square
am
by r.
telling that only.
So we'll get
In the
k
denominator,
equal
2
to
and 4 are multiplied. That's why 1 upon
yes
8 pi epsilon.
1 upon 8 pi epsilon naught e square by, this is the kinetic energy. Okay. So this is the kinetic energy we are getting. Okay.
Yes, sir.
Now what is the potential energy? Whose potential energy we are finding out? Whose kinetic energy we are finding out? The electron that is revolving around the nucleus. That electron kinetic energy which we are finding out. That is revolving in a orbit. And whose potential energy we are finding out? That electrons potential energy we are finding out. Getting? So what is
Yes,
the
sir.
potential energy? Potential energy just we discussed, that is K Q1 Q2 by R. So in this case, what is K? Q1 is electron, charge of electron. What is Q? Q2. Q2 is positive charge. Again, for hydrogen atom, it is E, and this Q1 is minus E, then distance between them is R. So we can write 1 by K value if I replace. So it is 4 pi epsilon naught E square by R. This is the potential energy. This is the potential energy I am getting, that is U equal to minus 1 by 4 pi epsilon naught E square by R. And kinetic energy I am getting 1 by 8 pi epsilon naught E square by R. This is the kinetic energy I am getting, and this is the
Yes,
potential
sir.
energy I am getting. Right. Now we can find the total energy of what? Total energy of, we are getting total energy of the electron which is revolving in orbit, right? So what will be the total energy? Total energy, how do we find? It's kinetic plus potential.
Yes, sir. We will just sum up those.
Yes. So what we'll get if we'll add kinetic plus potential here? Now kinetic energy is 1 by 8 pi epsilon naught R E square. Potential is minus E square 4 pi epsilon naught R. So if we'll subtract, what we'll get? E square 4 pi epsilon naught R is common. So it is 1 by 2 minus 1. So this one you will get half minus 1 is minus half. The total energy you are getting negative. That means attractive energy. So half minus 1 is minus half. So minus half you will multiply, it will be 8 pi epsilon naught R. This is the total energy you are getting. This is the total energy of the electron that is revolving around the nucleus. Right? This is the total energy of the electron
Yes, sir.
revolving around the nucleus. Now see the total energy. The total energy is minus E square 8 pi epsilon naught R. And what is the potential energy? Potential energy is minus E square 4 pi epsilon naught R. That means half of the potential energy is total energy. Right? Half of the
Yes, sir.
potential energy is total energy. And also, what is the kinetic energy and total energy relationship? What is the kinetic energy and total energy relationship? Okay. What is the relationship between the kinetic energy and total energy? Kinetic energy is E square by 8 pi epsilon naught R, and total energy
Yes, sir.
is getting E
Is
square.
negative E square upon 8 pi epsilon naught
So
R
we
only.
can write total energy is equal to minus of kinetic energy simply.
Yes, sir.
So if kinetic energy, sometimes very easy question given means are given in your board exam, simply kinetic energy will be given and it will be asked that what is total energy. So no need to use all these formulas. What you will do, you will simply write negative of that energy is the total energy, right?
Yes, sir.
So that is the case, right? How you should know that the relationship. So sometimes without calculation, simple thing will be given. You need to find the total energy.
Yes, sir.
Now you can try this example. 12.3. Example 12.3. So example 12.3 says what? It is found that experimentally 13.6 eV energy is required to separate a hydrogen atom into a proton and electron. So what is the construction of hydrogen atom? The construction of hydrogen atom is like it has a proton in the nucleus and an electron, right? This is a simple hydrogen atom. Now they are bound because proton is positive charge, this is negative charge, so electrostatic attraction is between them, they are bound. So how can you separate it? You have to provide energy to bond, break this bond, and this electron will be separated. That means whatever the energy electron has, that much of extra energy you have to provide it so that it will be broken and it will be separated, right? It will be broken and it will be
Yes, sir.
separated. So here, what is the energy of the electron? Now recently we calculated the energy of the electron, total energy of the electron is E square by 8 pi epsilon naught R. So if we put all these values, E value that is 1.6, and also it is given hydrogen atom. Okay, so later on we will see that the hydrogen atom, if we put all these values, we will be getting the first cell energy on the electron is in the first cell, not in excited state. If we calculate using everything, we will be getting it's 13.6 eV. What is the energy of the first electron cell? The hydrogen atom, if the electron is in the first cell, the energy of the hydrogen atom will be total energy is minus 13.6 eV. If you convert to joule, so how will you convert? You will multiply the 1.6 into 10 to the power minus 19,
Yes, sir.
so that it will be converted to joule. So 13.6 into 1.6 into 10 to the power minus 19. So it will become joule. So if you multiply, you will get this number. That is minus 2.2 into 10 to the power minus 18 joule. So this is the energy the electron is having, which is equal to this much. That minus 2.2 into 10 to the power minus 18 joule. This is the energy the electron is having. Now the question is that it is found experimentally that this is 13.6 eV energy is required to separate a hydrogen atom into a proton and electron. So this much of energy is required. That means this is the energy the electron, because we found the total energy this, so that means total energy must be equal to this much, right? So that it is able to break
Yes,
it.
sir.
Compute the orbital radius and velocity of the electron in a hydrogen atom. So we have to find what radius we have to find, and we have to find the velocity. So radius, simply you can put here energy. If we simplify this, you can easily get the radius, right? We can easily get the radius. How will you get the radius? Now simple, you just substitute E here, like radius will become minus E square by 8 pi epsilon naught E. Okay, 8 pi epsilon naught E. What is E here? E value is this one in joule. Remember, don't put the energy in EV in the formulas, because all the formula, mass, everything, radius, everything is given in SI unit, and EV is not Like joule is the SI unit, so you have to convert EV to joule when you are putting the energy in the formula. That one you keep in mind.
Yes, sir.
Okay. So R equal to E square minus E square by 8 pi epsilon naught E. So if you put the value of energy here, so what you will get? All this value E square, everything is put, all the values are put here, right? So after you put all the values, what you will get? You will be getting 5.3. You will multiply and you will check. You should get 5.3 into 10 to the power minus 11 meter. That means if this is the nucleus of the hydrogen, if this is the nucleus of the hydrogen, then this is nucleus and this is your having proton and electron revolve around it, right? Electron revolve around it. So what is the radius distance? This is the radius. So radius we are getting 5.3 into 10 to the power minus 11 meter. Clear? Then next part is find the velocity of the revolving electron. So how will you find velocity? Now if you go back to our last
So we
experiment,
know the relation R equals to K square by mv square.
hmm? Yes, we know the relation K
Yes, sir.
square by R equal to mv square, right? This is the relation we know. So we can find v square equal to Ke square by mr, or we can say v equal to under root K value we can put E square by K value if we'll put, what you will get? E square and K value if we'll put, it's 1 by 4 pi epsilon naught, and M value is 9 point, what is the mass of electron? 9 into 9.1 into 10 to the power minus 31 kg. And R, what is R? R is the this one. We already got the value. Put this value of R. That is 5.3 into 10 to the power minus 11. So E square, it will be come out of the root over. So it will be E. So B equal to, you will be get E by this one, or you can put the value of E as well, and you can find the square root. It should come approx. This calculation will be a little bit lengthy, but you have to approximate and
Yes, sir.
run the faster calculation. Like first you have to equate all these terms, then you have to use the numbers, right?
हाँ, yes, sir.
And like
E
1 by
को हम रूट के बाहर ले सकते हैं, वो एक ले सकते
you can take E outside of the root, right? So that it will come this one and it will be velocity. So it's meter per second.
हैं. Sure, sir.
It is meter per second.
Yes, sir.
Okay. So now atomic spectra. So like this type of numerical you can practice for the board exam. So what is spectra? Atomic spectra. Atomic spectra means what is the meaning of spectrum? Spectrum means a band, right? Suppose different wavelength light is coming up and will group together.
Yes, sir.
So this
Band
is
of
one
visible
band, this is
colors.
one band. So this is called spectrum. Like not discrete value, gradually, let's say it is increasing the wavelength. So this is a spectrum. Let's say red to violet to red. This is a spectrum of the wavelengths. So what is atomic spectra? Atomic spectra tells that if suppose this is a nucleus and electron is there, suppose it's a hydrogen atom, one proton, one electron. Now this electron can go to the excited state by gaining the energy. This is the ground state, let's say. It will gain the energy. You put UV light or some energy, you supply, it will gain and reach the higher excited state. When it will again jump and come back to the original state, it will again emit the energy. First, it will absorb the energy, it will go to the higher cell, and if it is in the excited state, it will go to the ground state or lower states by emitting the energy. So atomic spectra means when the electrons or the charged particles, they will let's say they will jump from the higher cell to lower cell, it will emit energy. How much energy it will emit? It will emit energy E equal to, or you can say EI minus EF equal to H nu. That we will discuss in the later part also in detail. So this much of energy
Yes, sir.
electron will release when it will jump from a higher cell to lower cell. So nu is the frequency, S is the Planck's constant.
Yes, sir.
Nu is the frequency. So when it is jumping from different, let's say 2 to 1 or 3 to 1, 2 to 1, so it will emit different amount of wavelength. Different wavelength, so the different frequency will come up. Because frequency dependent upon the wavelength. So it will emit a spectrum of different wavelengths. That is called atomic spectra. So each element has a characteristic spectrum of radiation which it emits. So each element has a different characteristics. Like hydrogen, what is the wavelength it is emitting? The helium may not emit the same amount, right? Each element has a characteristic spectrum of radiation which it emits. When an atomic gas or vapor is excited at low pressure, usually by passing an electric current through it, it emitted radiation has a spectrum which contains certain specific wavelengths only. So it emits the only some specific wavelengths, but this is, let's say, at a particular, let's say 500 nanometer, 600 nanometer, 700. So this is called spectrum of wavelength. This is called spectrum of wavelengths. So a spectrum of this kind is termed as emission of line spectrum, and it consists of bright lines on a dark background. Bright lines on a dark background. The spectrum emitted by atomic hydrogen is shown in the figure 12.5. So you can see this series. This is for a hydrogen emission line spectrum for hydrogen atom. So spectrum means we have given them some like names like Lyman series, Balmer series, Paskin series, all this. So what is Lyman series? Lyman series means the first series that suppose the nucleus is here and the electron is here. Now electron will jump from, it can jump from second state to first state. It can jump from second excited state to again n equal to 1 ground state. So when it will jump from always to 1, like third to 1, fourth to 1. So when it will jump to 1, whatever the wavelength it will emit, that all wavelengths are kept under one group that is called Lyman series. So it will vary from 91 nanometer to 122 nanometer. So this is called the spectrum or Lyman series spectrum. Similarly, when the electron will jump from third to 2 or fourth to 2, fifth to 2, sixth to 2, when all the jumps are from 2, means EI can be greater than 2, but EF to second orbit, then we name it Balmer series. In that range, 360 nanometer to 650 nanometer, the wavelength will be emitted. So we name that series as Balmer series. That emission, we can say these are the spectral lines of different wavelengths we are getting when electrons are jumping to second orbit. That we are naming it Balmer series. We are naming it Balmer series. Right? Study of emission line spectra of a material can therefore serve as a type of fingerprint for the identification of the gas. When white light passes through the gas and we analyze the transmitted light using spectrometer, we find some dark lines in the spectrum. These dark lines correspond to precisely to those wavelengths which are found in the emission line spectrum of the gas. This is called absorption spectrum of the material of a gas. So there can be emission spectra, there can be absorption spectra. Like absorption, when it will absorb the energy, and that will be the absorption spectrum. And emission spectrum, when it will jump from higher to lower, it will be emission spectrum. Bohr's model of hydrogen atom. Now we have discussed that what are the shortcomings or what are the problems in the Rutherford models. What are the shortcomings or problems in the Rutherford model, right? Rutherford told that the electrons revolve in around the nucleus, like the planet revolve around the nucleus. The planet revolve around the nucleus. But the problem is that when the electrons revolve around the nucleus, we have already discussed that it will emit energy. When it will emit energy, gradually it will gradually lose the energy, and due to that, it will not be in that orbit. It will gradually come, like these electrons will, after losing energy, gradually the radius will become slow, and finally they will come and fall on the nucleus. But that does not happen, because an accelerated atomic electron must spiral into the nucleus as it loses energy. So in reality, it is by experimental verification, we got that the electrons, they do not come into the nucleus, and if it will fall on the atomic nucleus, like that will collapse, right? So but atom as a whole remains neutral. So we thought that when people started thinking that electrons are in certain orbits, So Rutherford gave a model for that. Rutherford gave a model for that. That is called Rutherford atomic model. And this is the beginning of your quantum. This is the beginning of your quantum treatment. This is the beginning of your quantum mechanics, right? Or so Bohr's used the theory that is called quantum theory. So what Bohr told? What is Bohr's atomic model? Now, as per Bohr's atomic model or Bohr's first postulate, it comes in the exam. What is Bohr's postulate? First postulate. So Bohr's first postulate tells that an electron in an atom could receive or could revolve in certain stable orbits without emission of radiation energy. Right? So what Bohr argued or Bohr gave the postulate that suppose nucleus is there, so electrons can revolve around the nucleus in stable orbits. Right? It will not emit energy and it will just fall on the nucleus. Rather, it will revolve in stable orbits. So this is what Bohr told in his first postulate. It comes. According to his postulate, each atom has a certain definite stable states in which it can exist, and each possible state has definite total energy. So it's not indefinite, it's a fixed amount of energy when the electrons are revolving and around the nucleus. It will revolve around the nucleus in fixed energy levels. So this is the first postulate the Bohr gave. So these are called stationary states of an atom. What it is called? It is called stationary states. And these orbits are possible, Bohr's second postulate tells, these orbits are possible whose angular momentum, already I have told you, whose angular momentum is L is n into h by 2 pi. It's a integral multiple of h by 2 pi. This is the discrete, that he gave the idea that energy levels are discrete. And if energy level are discrete, then we can say like it's a packet form, or you can say it is having stable orbits at different, like electrons are at different distances, particular fixed distances. So fixed orbits are there. So from here, let's say the electron first orbit is here, definite it will have a second orbit like at a fixed radius, not a variable radius, sometimes here, sometimes here, not. It has a fixed radius, so electrons will be available at the fixed radius, right? Electrons will be available at the fixed radius. And we can write that this L, this angular momentum, as the electron revolve around the nucleus, this angular momentum will be what? Angular momentum, we know the formula for the angular momentum, that angular momentum is, we know the formula for angular momentum. Angular momentum is R cross P. P is the linear momentum, R is the distance from the axis. It is revolving. It will revolving around the let's say distance R. So you will write it is RP if they are perpendicular to each other. So simply RP, or you can say P is MB. So simply L is MBR. So only those orbits are possible whose MBR or angular momentum is NH by 2 pi. So we can find the radius from here. That R will be NH by, or you can say, we can find this concept NH by 2 pi. R is NH by 2 pi MB. So only second postulate tells us Bohr's second postulate defines these stable orbits. This postulate states that electron revolves around the nucleus only in those orbits for which the angular momentum is some angular multiple of h by 2 pi. So Bohr's second postulate tells what? Now these stable orbits, where these orbits will be location? What is the location of the orbits? And the location of the orbits will be, it will be the angular momentum of the electrons should satisfy this nh by 2 pi, and from here we can calculate what will be the orbits for different energy levels where the possibilities of electrons will be there. This postulate states that electrons revolve around the nucleus only in those orbits for which the angular momentum is some integral multiple of h by 2 pi, where h is the Planck's constant. Planck's constant value is h equal to 6.6 into 10 to the power minus 34 joule second. This is the Planck's constant value. This angular momentum L of the orbiting electron is quantized, that is L equal to nh by 2 pi. So quantized means distinct, like separate. So here orbits are not like they are not. So one orbit overlapping other orbit, it's not like that. They are at a fixed distance and they are stationary. This stationary electron revolves in those stationary orbits. So we'll discuss till the last postulate of the Bohr's model, then we'll discuss in some other class. So Bohr's third postulate tells that if I've already told you, if electron is jumping from the higher cell to lower cell, it will emit the energy. That energy emission is EI minus EF, that is h nu. So it will emit the amount of energy that is h nu. It will emit h nu amount of energy. So Bohr's postulate incorporated into atomic theory the early quantum concepts that had been developed by Planck and Einstein. It states that an electron might make a transition from one of its specified non-radiating orbits to another lower energy. So it can jump. When it does so, a photon is emitted having energy equal to the energy difference between the initial and final state. So we know that when the light will emit, light quanta or the particle is photon. Photon is the light particle or the quanta of the particle. So it will have the energy that is h nu. And we can find from the h nu the wavelength, because we know h nu is equal to nu is the frequency and that is c by lambda. hc by lambda. So from here we can find what is the wavelength of the light, but that is emitting from the in this transition, right? So these are the three postulates that Bohr gave, and this is the modern theory of the atomic structure, that how and where, what is the energy of the electron and how these electrons are revolving and where they are revolving, from how much distance they are, from how much distance from the nucleus they are revolving, right? So all these things are there, explained by the Bohr in its postulates, right? So let us stop here. We will be discussing in the next part 2, the rest part of this chapter. So rest part of the chapter means again the energy calculations and radius calculation. All these things are there, and also the second quantization of theory of the Bohr is also there. So all these things we'll be discussing in the next class. Thank you for watching.